Parallel resistance. Resistors are in parallel when there is more than one path for current to flow. Similar to an intersection when you are driving, where there is more than one road you can turn onto. So looking at this circuit here, IT is out of the source and is measured between points A and B and also between points F and E. Current I1 is measured between nodes B and F, which is right here. I2 is measured between nodes C and G, and finally I3 is measured between D and H and G. Between nodes B and C is a current that adds up to I2 plus I3. This same current is also between nodes G and F. So let me back up a little bit here. So that's right here. This current here between B and C and G and F, this current goes in, splits up between 2 and 3. Some goes down here, some goes down here. And then at point G, it's recombined and travels through this section here. So those are the same. Using Kirchhoff's current law. So Kirchhoff's voltage law is for series circuits, and Kirchhoff's current law is for parallel circuits. Two equations can be written from the above example. IT is equal to I1 plus I2 plus I3, and IX, that's that top current between, or that divides between 2 and 3, IX is equal to I2 plus I3. So I use Kirchhoff's current law to write equal current equations and Kirchhoff's voltage law to write voltage equations. Parallel circuits have, now these are the things that parallel circuits have that series circuits don't. Parallel circuits have different resistor currents, assuming the resistors are all different. Obviously, if you have two parallel resistors that are the same number or the same value, they're going to have the same current through them. But they basically have different resistor currents. Whereas series circuits have the same current because it's the same current that travels through all the resistors. Now, parallel circuits likewise have the same voltage across the parallel components, vice versa for series circuits. Series circuits all have different voltages. The total parallel resistance is always less than the smallest resistor in parallel. So this is a good check that you can use when you have resistors in parallel and you use the formula to calculate the parallel resistance. The total parallel resistance must always be less than the smallest resistor in parallel. So if it doesn't come out less than that number, you did the math wrong. Okay, this is different from series circuits. Series circuits, the resistors have the same current and different voltages. Let's calculate total resistance in parallel. Alright, so here I have a circuit. I have current comes out and divides three ways. So I have 1K, 2K, and 3K in parallel. So when I write it, I'll write it in a sentence first. I have 1K in parallel with 2K in parallel with 3K. Then I have it in terms of symbols. RTP, which is total parallel resistance, is equal to 1K, and then these two lines here, that means parallel. So 1K in parallel with 2K in parallel with 3K. So RTP again is the total parallel resistance. So the math that's involved when you do this is reciprocal formula. It's 1 divided by 1 over 1K plus 1 over 2K plus 1 over 3K. And 1 over the resistor is conductance, so it's actually 1 over the conductance of resistor 1 plus the conductance of resistor 2 plus the conductance of resistor 3. Calculator strokes. So first of all, you want to be in the ENG mode. Then that way it'll automatically put your answers in terms of K metric prefixes. You just have to transfer it. So you have your 1 over X key. So you can look for that on your calculators. Everybody has different calculators, but most calculators will say 1 divided by X as a special key, or it might even have X to the minus 1 power will be the key. So you start here, you go 1 EE3, that means the 1K, 1 over X, that takes the inverse of it. So far in the formula, I just did this right here, 1 over 1K. Alright, plus 2 EE3, 1 over X, plus 3EE3 1 over x. So the 2EE3 is the 2k inverse. The 3EE3 is the 3k inverse. Then equals, it's very important you have to hit the equal sign here once you do this to all the resistors. Then you take the final 1 over x. That final 1 over x, looking at my formula here, that's this one right here. Okay, so if you use the 1 over x key, you do not need to use the division key. Yeah, so don't go 1 divided by, you don't need that. Using Ohm's law, we can calculate branch currents. Remember, parallel resistors have the same voltage across them. Given the circuit, find the current through each resistor. Okay, and IT. So here we have a 2K, a 3K, and a 2.5K, 10 volts. This 10 volts from end to end is connected across resistor 1, 2, 3. You can see that each top point of the resistor is directly connected to the source, and each bottom point of the resistor is connected to the bottom of the source, so they all have 10 volts. All resistors, because they are in parallel and the voltage source from end to end appears across each resistor, they all have 10 volts across it. So V1 is equal to V2, which is equal to V3, which is equal to VT, which is equal to 10. Using Ohm's law to solve this, since I know the voltage across the resistor and the resistor, I just need to divide. So 10 over 2K gives me 5 milliamps. That's my first current. 10 over 3K gives me 3.3 milliamps, and 10 over 2.5K gives me 4 milliamps. Notice I did not need total resistance to solve this. And using Kirchhoff's current law, I just add the currents up and I get 12.3 milliamps. If RT was found, again, that 1 over 1 over formula, so it would be 2EE3 1 over x plus 3EE3 1 over x plus 2.5EE3 1 over x equals 1 over x. That would equal 810 ohms. Notice the 810 ohms is less than the 2K, so that's just a little check for myself to make sure I did the math. So then I would take 10 volts over that total resistance, which gives me 12.3 milliamps. And that is the same as it was when I added them up. With the RTP total parallel resistance of 810.81 and IT current, the current divider formula can be used. So this is the second way of trying to find currents. Current divider formula can be used to find the same numbers for the branch currents that I found using Ohm's law above. It's always easy to use Ohm's law, but if you use current dividers is very similar to voltage dividers. Basically, you're taking ratio of resistors. But since the total parallel resistance is smaller than any of the resistors, that's now in the numerator. So it's total parallel resistance divided by any one of the branch currents times total current. That'll give me my branch that I'm looking for. So I say any branch current is IX, total parallel resistance is RTP. Resistance associated with branch, Rx is the resistance associated with the branch that you're trying to find, and total current is IT. So from the same example above, for branch 1, total parallel, so it's 810. R1 was 2K. IT I found before was 12.3, so that gives me 4.99. I think when I use Ohm's law I got 5. For I2, again, total parallel is 810 over R2 is 3K times 12.3 milliamps. I get 3.3 milliamps. And for I3, 810 over 2.5K times 12.3 is 4 milliamps. So these all are the same numbers. So using current dividers, you do not need to know voltages across the resistors. Current dividers are used in parallel circuits, and the voltage divider formula from Chapter 5 is used in series circuits, so you don't want to use a voltage divider formula for parallel. Power in parallel circuit is the same process as a series circuit. Basically, you have 3 formulas: voltage times current. So if I'm looking for power 1 dissipated by the first resistor, I would use voltage 1, current 1. Power 2, voltage 2, current 2. Power 3, voltage 3, current 3. You need V1 and I1, or you need V2 and I2. Here you need V3 and I3. Or then the second set of formulas, I squared R. So again, you just use all the same quantities that are associated with each resistor. Or excuse me, V squared over R. So we can use any one of these three formulas to get the same answer. Any of these formulas can be used. Just make sure you are using the quantities that belong with each component. So I will use one of each formula to find the three powers from the above example. So the first formula I'll use is P1 equals V1I1. So the voltage across resistor 1 was 10, current 1 was 5, so P1 is 50 milliwatts. Now if I'm going to use I squared R, current through resistor 2 was 3.3 milliamps. I square that times 3K, I get 33.27 milliwatts. Keystrokes for this one, so here's my current, 3.3 EE, plus or minus because I have to do the milliamps, so I have to hit my plus minus key. This is not the addition subtraction key, this is a separate key. 3, then they have an x squared key. This is the multiplication key. I'm multiplying by 3K, so it's 3EE3 equals, and that should come out to 33.27 milliwatts. And the last formula is V squared over R, so again I'm using V3, and V3 is still 10. They're all in parallel, they all have the same voltage. So I square 10 divided by 2.5K, I get 40 milliwatts. The sum of all powers equals total power, so I can just add those up, get total power. Or I could actually use this formula. I can use any one of the three formulas, but this one here, voltage total I total, voltage total is still 10. I total is my total current, and notice the two numbers are exactly the same. So either way. Calculating an unknown resistor in parallel. Example. So here I know total resistance and I know one resistor. I don't know the other resistor value, so I'm looking for the other resistor value. So find R2 given R1 and RT. So this one looks like this. RT is 200, R1 is 600. I don't know RT, so here's the formula. R2 is resistor 1 times total, resistor 1 minus total. So 600 times 200 divided by 600 minus 200. So that comes out to 300. And I guess that's it. That's it.